While trying to predict the orbit of the asteroid Ceres, based only on a limited number of observations over a 6-week period at the beginning of 1801, Johann Carl Friedrich Gauss applied a method that became known as divide and conquer to take advantage of the inherent symmetries in the polynomials he was calculating. In the days before computers, this method, although useful to Gauss, was of limited use to everyone else, and lay largely forgotten until Cooley and Tukey rediscovered it in the early 1960s, whilst trying to find a way to take advantage of the symmetries of sines and cosines to make the discrete Fourier transform easier to calculate. But how does divide and conquer work? And how does it make not only calculating the DFT more efficient, but many other tasks as well? These are the questions we're going to try and answer over the next 2 videos. To get started, let's set aside the DFT for a moment and focus on an easier problem that will also benefit from a bit of divide and conquer. The task is to sort this array of 8 numbers from smallest to largest. One possible approach is to take each number, compare it to the next in the array, and swap the numbers if the second number is smaller than the first. This method is called bubble sort because with each pass through the array, the largest unsorted element bubbles up to its correct position, much like a bubble rising to the surface. However, this method requires multiple passes through the array, and we often find ourselves rechecking values that have already been sorted. While simple, bubble sort is not very efficient. It requires 42 compare operations and 20 swap operations, giving a total of 62 operations to sort just these 8 numbers. Now let's try a different approach, one of several methods that employ the divide and conquer strategy. The particular method I want to demonstrate here is called merge sort, which is much more efficient. Here's how it works. The first step is to divide the array into 2 halves. For example, if the array contains 8 values, the first 4 values form one subarray, and the last 4 values form the other. This division process continues recursively. Each subarray is split into smaller subarrays until we are left with individual arrays containing only 2 elements. In the standard merge sort algorithm, this process would typically continue until each array contained only a single element. However, to maintain consistency with the divide and conquer approach used in the Fourier transform, I've chosen to stop the division at arrays containing 2 elements. Once the array is fully divided, the next step is to conquer the problem by sorting each small array. Since each array now contains only 2 elements, this step involves comparing the 2 numbers and swapping them if necessary, so that the smaller number is in the first position and the larger in the second. The final step is to combine these sorted subarrays, merging them back together while maintaining the order. This involves repeatedly merging 2 sorted arrays into one larger sorted array. During each merge, values from both arrays are compared, and the smallest value is placed into the resulting array first, followed by the next smallest, and so on. Only one pass is required to merge each pair of arrays, because the arrays were already sorted during earlier stages. This merging process is repeated until we have a single array containing all the original values, now sorted from smallest to largest. If we count up all the divide, compare, swap and merge operations, the total number of operations is now significantly lower, 42 operations for this example compared to bubble sort's 62. By ensuring that the smaller arrays are sorted before merging them into larger arrays, we avoid the need for multiple passes through the data. In other words, the results from work done in one stage are reused in the next, saving us from having to do the same work again. This is the essence of divide and conquer, breaking the problem down into smaller, more manageable parts, which makes solving each part very simple, and combining the solutions to get the final result. So we can identify 3 distinct stages in the algorithm: divide, conquer, and combine. The beauty of this approach lies in its recursive nature, which not only simplifies the logic, but also makes it very easy to implement in code. The divide and conquer function repeatedly calls itself, breaking the problem down into smaller and smaller pieces. Then, as each nested call returns to its parent function, the results are combined step by step until the whole task is complete. This foundational logic forms the backbone of the Cooley-Tukey FFT algorithm. But how do we apply this divide and conquer approach to the discrete Fourier transform?